Hey everyone, welcome to the programming tutorial for the KeebCard. In this tutorial we're going to go over the structure of the KeebCard project as a whole and how I've written a Conway's Game of Life simulator for it. I've done my best to make this tutorial beginner friendly, but it's not a nuts and bolts on how to program microcontrollers because there are much better sources of information for that topic than myself. I recommend having a base level knowledge of programming and C in general before watching this tutorial. If you don't though, I don't know, stick around, you might learn something. So let's get into it. We'll start with the INO file, which is the base of the project. This is keepcard.ino. So to understand this file, we need to understand a little bit about the Arduino suite. When programming in C, you normally use what's called a compiler, which takes the code you've written and the target machine you want it to run on and translates it into commands that the machine can understand. That still happens when you are using the Arduino suite, but it's hidden away from you. Arduino handles any sort of compiler configuration you need and allows you to pull in libraries and targets easily. I chose it because we'd have much more control with a traditional compiler setup, but it would be a lot less accessible and a lot less portable. Arduino files start with an INO file that defines two methods, setup and loop. And those are down here somewhere. Setup and loop. Setup runs first, and then loop runs continuously. This makes it easy to create a program that automatically updates if you are taking the temperature from a temperature probe and displaying it on a screen, for instance. With the way the code is written right now, we only use the setup function. You can actually see that the loop does not do anything. And we have our own loop functions that run inside of it. That might change later, but if anything, we'd probably use the loop to set up a new game every time the last game ends. It would take a lot of work to get our loops into the main loop function. What's more likely to happen is I might break out multiple INO files for each project to separate them a bit more. Right now, though, in order to choose a program to use, you uncomment one of these defines here. Defines are macros, these defines are macros, which is one of the things that we probably shouldn't get into in this tutorial. Just know that when we define Conway here, later on, if we write ifdef Conway or defined Conway, the code inside of that block will run. That's right here. So that code runs this kind of structure here is why it runs. It contains this. So we already switched it to Conway. So now any code that looks to see if this macro exists will run. Conway.h right here is what's called a header file, which defines the interface for the CPP file that we've defined. So that's these two files up here. This is the header file. This is the CPP file. We'll be getting to those. So let's see. This project uses C++, hence the file name CPP. But beyond classes, it doesn't take much advantage of the extra features C++ affords us. When we include the header file, that's telling Arduino that we want to use the CPP file we have and what kinds of things that file contains. It's not quite the same, but you can basically think of it as copy-pasting both the header file and the CPP file right here. The way our INO file works is in setup, we call universal setup to do anything we have to do for every game, and then we call setup game, which has the logic to set up whatever specific game we've chosen. If we look at universal setup, we see this OLED object. This represents our connection to the OLED screen, and it is created and instantiated and managed by the Tiny4K OLED library. We'll go over some of the functionality in this tutorial, but if you want to write your own program, I encourage you to take a peek at the Tiny4K OLED GitHub, which is here. The interface is pretty well thought out. Back to the code. So anyways, this function initializes the screen. It tells us what font we want it to use. It switches the render frame so that we can take advantage of double buffering. It clears the screen entirely. It turns on the display. It seeds the random number generator so it creates different games. It sets the switches to be inputs. And it has a patch for Snake since Snake doesn't use double buffering. And that should probably go down in the other section. So I know that's a lot, but most of it is pretty uninteresting, and it happens for every game. One thing I'll mention is that computers are very bad at generating random numbers, and they usually use some form of entropy input to help them. This can be a light sensor, the time, an accelerometer reading, basically anything that you don't really know what the value is going to be. In our case, we don't have a good source of entropy. We have a clock, but it always starts at 0 when you start up, and by the time it gets to this line, it's always the same value. Um, we use the analog output from the middle button, which is held high by a pull-up resistor, but it still varies a little bit. I'm working on getting an entropy library based off of clock jitter, but because of how Arduino pulls in dependencies, it makes stake fail to load, fun fact. So we'll get that working at some point. The one other thing to talk about, hold on. The one other thing to talk about is double buffering. We have a 128 by 32 OLED screen driven by an SSD 1306 OLED driver. That driver actually has twice as much screen memory as the screen has pixels. It's actually made to drive 128 by 64 OLED screens. So the Tiny 4K OLED library had the great idea of using that memory to implement double buffering. When we want to show an image on the display, we first have to tell the screen what to show, and then the screen shows it. We do this by writing to the screen one byte at a time. Unfortunately, with our microcontroller, we write so slow that you can actually see those clusters of pixels changing on the screen. The solution is we actually have two places where we tell the screen what to show. While the screen shows one of those images, we write to the other one, and when we're done, we tell the screen to show that one instead. This gets rid of the flickering, but it's not necessary in all cases. For Conway, though, it works great, so we're going to stick with it. So now we're going to go to Setup Game, which is going to look complicated, but it's actually very simple. So if you remember that defined from before, the only code that will run is the code underneath whatever you've defined. And so that is going to be right here. So we are going to run these 3 lines. So in our case, all we do is we make sure we're in horizontal memory addressing mode, we instantiate a Conway game, and then we tell it to run. We won't go too far into memory addressing modes, but suffice it to say, there's 3 different ways you can update the screen with our driver. Since we update the screen in bytes, sometimes changing the memory addressing mode makes updating the screen a lot faster. For Pong, we set the memory addressing mode to vertical because the paddles are vertical, which saves us a ton of time when we want to re-render them. For Conway, we have to update the whole screen every frame, so we just leave it in horizontal addressing mode. If you write your own program, you'll want to think about what memory addressing mode you use. You can use any one you want, but depending on how their game renders, you could get a massive speed boost picking one over the other. It's also worth noting that many of the nicest parts of the Tiny 4K OLED library are meant to work in horizontal addressing mode only. Alright, let's look at Conway.h. At the bottom, you will notice the interface for the Conway class. That's just telling us what functions exist in the class, what arguments they take, and what their return types are. You'll also notice these structs up at the top. Structs are kind of like classes 1.0. They don't have any methods, but they are clusters of data that are usually related. We have three structs, uPosition, position, and bitrow. But we don't actually end up using bitrow, so don't even look at it. uPosition and position are used for position information on an XY grid. The U stands for unsigned. It means that you can't have any negative numbers in either of these members here. I'm not going to go into types too much. I'm definitely not the best person to ask. But these 8s mean that these are 8-bit integers. So the signed integers go from negative 128 to 127, and the unsigned integers go from 0 to 255. And this is because 2 to the 8th is 256. So if your number is ever outside of these ranges, it actually wraps around. So if you had an 8-bit unsigned integer and it went to 256, it would actually be 0. And if it was signed, it would be, you went to positive 128, it would actually be negative 128. If the number is ever outside, yeah, it wraps around. This is a common scenario that you'll have to think about There are N16s and N32s as well, so it's mostly just about choosing the right one. But if you are writing your own programs, you will have to think about this a bit. So you'll see some constants here, and you'll see them used in the interface definition below. Constants are numbers that never change. We use these to set the size of the board and board rows and similar. You can't set the board to an arbitrary size right now in the code, but it's good to have these separated in case we need to rework them later. One other thing to note is this notation here, which is called bit shifting. So I'm bit shifting the board size by 3 bits, essentially removing the first 3 bits of the number, sliding all the other bits down, and putting 3 zeros at the top of the number. This sounds complicated, but we're using it for a specific task. This bit shift divides the number by 8, removing the quotient. Or the remainder? Removing the remainder. The reason we do this is a microcontroller we're using doesn't have an operation for division, so it can be very expensive. Bit shifting is not exactly the same as division, but it's much faster. So if we know for sure that it works in our scenario, we might as well use it instead. The compiler should be smart enough in this case to realize that bit shifting works, but you never know, so why not? So now let's look at the implementation of the Conway class. Conceptually, our Conway program works by having 2 boards, which you can see here and here. One is much larger than the other. These 2 boards are the previous board and the current board, or, I guess it's the current board and the next board. They kind of swap around a little bit. Each turn, or tick, so to speak, we use the last tick's board to calculate a new board, and then we copy that board into the old board's place, transmit it to the screen, and then tell the screen to display it. Then we start that all over again. That's the whole program. That's everything that happens, and that's everything that we're going to talk about probably for the next hour. So if you haven't heard of Conway's Game of Life, it is a cellular simulator with very simple rules that gives birth to incredibly complicated structures. I'll link the Wikipedia article in the description, but basically there is an infinite grid of cells. The neighbors of a cell are all the surrounding cells that touch it, so all 8. If exactly 3 neighboring cells are alive, the middle cell springs to life, or it stays alive if it's already alive. If there are 4 or more, or 1 or less neighbors alive, the middle cell dies, and if it was dead, it remains dead. Any other outcome, the cell just remains the same, whether it's dead or it's alive. These simple rules make for pretty crazy patterns and shapes, and Conway's Game of Life is actually Turing complete, which means, in a nutshell, it means that with infinite elbow grease, you could do anything you could do in any other programming language in Conway's Game of Life. For our purposes, though, we are extremely memory constrained, so that's not really what we're going for. So you can see up at the top here, we instantiate the board in the new board. The contents of the first board is what's called a glider gun, and the new board is all zeros. That's shorthand right there, because the first thing we do is we write over it, so it doesn't matter. You don't have to, don't even try to understand this. All of the 1s are alive pixels, all of the 0s are dead pixels, but we'll get into this format a little bit more. Let me see. So these are static variables, which means that they are local to this file and they do not reset. Honestly, there's probably a better way of doing this, but declaring them static means their memory gets summed up and reported when you compile an Arduino, which is very helpful to know how much memory you have left. So this function here is a constructor, and it runs when the class is instantiated. All it does is saves a reference to the OLED that we use in the INO file. This is actually a pointer, which you can tell by this little star here, which is way outside of the scope of this tutorial. But just know that instead of using periods to toggle the screen, we would do stuff like, here, let's see, if we go back up here, yeah, OLED dot on. We are actually going to be using little arrows instead, which you will see below at some point. So the real meat starts happening in run, though it doesn't look like very much. I prefer small functions that do one thing with a very clear name, so that's what I went with in this program. So this loop right here, while true, runs endlessly. And so as soon as you're done running these 2 lines of code, we immediately run them again, and that happens forever until you turn off the device. Update game is tasked with updating the game state, and update screen is tasked with telling the screen about the new game state that we just updated. So update game visits each cell, and that's what we're doing here. We are looping over the board, and we are calling update cell on every cell. Then after it's done, it calls update board. It's safe to assume that update cell, It's safe to assume that update cell gets each cell in the new board ready. So if you look at update board, this is where we copy row for row the new board over to the old board. And that would, for each row, old board's row equals new board row. So if you step out one more step, you'll notice that this completes update game, which means right after we copy over the board, we then update the screen. If you look at update cell, it gets the number of living neighbors for that cell in the original board, and it uses that number to set the value of the new cell in the new board via the set cell function. These if statements here are just what I explained earlier as to whether a cell springs to life, dies, or remains the same. So get living neighbors is probably the most complicated game logic that we have. You can see these position deltas here and how they are laid out in a grid. If you think of the middle of this as the cell in question, that's this one, and that's what we're passing here. If you think of this, the middle of this as the cell in question, if you added each of these deltas to the position of this cell, you would get the position of that specific neighboring cell. You don't have to organize it in a grid like this, but I did it for clarity's sake. Notice that this is exactly what we do. We loop over each of these deltas. We add them to the position of the original cell, and then we call get cell on them to get the value. And we add its return value to the number of neighbors. We also short circuit right here. If we've counted more than 3 cells, we can actually save a little bit of time and stop counting, since we know the cell is going to die. And so then right afterwards we return living neighbors. So getCell always returns a 0 or a 1, and it always returns whether or not the neighbor is alive or dead. So when we add them up, we know the number of living neighbors. So obviously getCell gets the value of a cell at a specific position. If you have a board and the cell at row 3, column 4 is on, calling getCell with a y of 2 and an x of 3 would get you a 1. This is because arrays start at 0, but this row column, when you're telling somebody about row 1, column 1, you mean the top left cell in the table. So that is actually, that top left cell is actually x0, y0. If that cell was off, you would get a 0. How this actually happens is a little complex because of the bit packing we were talking about earlier, which we didn't talk about. These boards, as you'll notice, are actually whole bytes. There are 8 of these zeros here, and you can see that, like I was talking about how the ones are on pixels. You can't actually, where are we? Do we actually talk about this? No, we don't. Okay, so you can't actually set, you can't have a bit of information. You could make a type that would have a bit of information, but the absolute minimum possible amount of information that you can manipulate at one time on this microcontroller is 8 bits. And so this is kind of like if you've heard, 64-bit machines and 32-bit machines. We have a much smaller machine. We have an 8-bit machine. But basically that is the smallest block of data that you can manipulate. So what you can do is, instead of manipulating 1 bit at a time, you manipulate a byte 8 bits at a time. So we've kind of packed into this byte 8 pixels that we care about, that we want to change. So let's get back down here to get cell. So we start this program by making sure that the position we get is a valid position. That's this code right here. We do this because we indiscriminately check the neighboring cells, even on the outside of the grid. So sometimes we ask for the value of a cell that doesn't even exist. While a true game of life takes place on an infinite board, we can't even pretend to accommodate that with the amount of RAM that we have. In our case, we've decided that anything that isn't on the grid is always permanently dead. So if the position we ask for doesn't exist, we just return a 0. Next, we find what I call the boundary position of our cell by calling position to row index. So far, all the positions we've been talking about are theoretical positions on an x by y sized grid of bits. As you know, though, we don't have an x by y sized grid of bits. We have a single array of bytes. Position to row index answers the question of what byte in the array is the home to this position in the theoretical grid. This is the heaviest thing that we haven't glossed over yet, so if you're confused, don't worry too much. I wrote this, I made sure it worked, and I was like, man, I'm glad I don't have to do that anymore. So now that we have the byte that houses our bit, we still have to get the value of that bit in isolation. And so how we do that is, first off, we find the y value inside the row, which is this, and then we use this little bit of magic right here. So the first part of this grabs the whole byte we were talking about, which is right here. The second part uses a bit mask to make all the bits we don't care about 0. And so that is this right here. This is a bit mask. So basically what we're doing is we're taking the 1, we're using that bit shifting, so we're making a byte where only one bit is 1, and it's a specific bit that we care about. These 7s are actually because I just recently implemented this. The numbers in the grids are now big endian. And if you don't understand that, don't worry about it. It means that I think the most significant, or the least significant bit is to the left. And that is different than, I think, all of the other programs that we have. So I had to flip these around. Anyways, where are we? Yep. So the second part uses that bit mask to make all the bits that we don't care about 0, and then the final part, which is this, uses bit shifting again to slide the bit that we do care about to be the very first bit. If that bit was on, then this return, this number that we're returning from this function, is the number 1. If it was off, it's 0. And so this line is how we make it so that getCell only returns 1 or 0. So this video is already super long, so suffice it to say that setCell, which is right down here, does the same stuff that getCell does, but instead of returning the value at that particular bit, we set it. That is this magical row and this magical row. This magical row here. So we use what I call a nega mask here, which nobody else calls that. It's the opposite of the one that we use in a get cell. We make only the bit we care about 0, and all other bits stay the same. Then we inject the new value in with this code here. And then we actually reset the row inside of the board here. So to recap, we have visited every cell in the old grid. We've added up all of its neighbors to figure out what its new value should be. And then in the new grid, we have set that value right where it is in the old grid. We did this until there were no more cells to visit, and then we copied that brand new board over to the old board, erasing the old board. And that is all of this stuff that we just talked about, all up here. So now we have a completely new board. Everything's great. We've advanced one tick. We need to inform the screen that that's just happened, and it needs to show the new board. So this is where update screen comes in. So we are going to go all the way down to update screen. So we are getting close. Update screen is going to look scary, but because of an optimization I did, it's actually pretty simple. We need to store a single bit per cell in our grid. But after that, we have a lot of freedom as to how we store those bits. I decided to store them so that the first 8 bits are the first 8 cells in the first column. The next 8 bits are the first 8 cells in the next column. This continues until you get all the way to the right of the board. Then, after that, the next the next 8 bits are the second 8 cells in the first column. And the pattern continues. We did this because it's exactly how the horizontal memory addressing mode works in the SSD 1306 OLED driver. Starting with the top left pixel, it will update the first 8 pixels in that column, and then the first 8 pixels in the next column. You get the idea. Since we store the data in the same way it is displayed, it makes it much easier to display that data. There is one catch, though. We actually don't have enough RAM to make a full 128 by 32 pixel grid. In fact, we'd need twice as much memory just to house the 2 boards if that were the case. Instead, if you remember the constants from the header file, our grid is 64 by 16, which is 1/4 the size. We'll have to stretch the pixels out to display them, but since the board is exactly 1/4 the size of the screen, we can just make each pixel a block of 4 pixels. So that is what we're doing all over here. Actually, all over here. You'll notice we loop across the board and grab a row. So that is here. You might notice we're looping over board Y divided by 4, that's this bit shift, instead of 8. That's because we'll need to visit each byte in our array twice, since each 1/8 byte is actually a 2/16 swatch of pixels now, because we're multiplying everything by 2 and we're making each pixel, each bit, sorry, we're making each bit a 2x2 block of pixels. But we can only transmit 8 pixels at a time, and when we do, we automatically advance to the next column, if you remember. So that's what this code is about. When x is 0 and y is 0, we'll grab the first byte. We'll grab the first byte here. No. When x is 0 and y is 0, we'll grab the first byte here. And then bottom of data will actually be 1. When x is 0 and y is 1, a full 64 iterations later, we'll grab the first byte again, but bottom of data will be 0. So we'll bit shift 4 places when bottom of data is 1, meaning that we overwrite the bottom 4 numbers of the byte with the top 4. And so that's kind of how, we need to visit that number twice, and we need to get those 2 sets of 4, because we can only transmit 8 at a time. And that's how we do that. The next line here looks super crazy, but all it's doing, and it's wrapping all the way around. Can we do... Nah, I can't get it. All it's doing is doubling our 4 digits, actually. So if we had 1010, for instance, it would produce 11001100. This stretches the 4 pixels into 8 pixels, making each effectively a 1x2 pixel swatch. Relatedly, when we send the data to the screen, we actually send it twice. This stretches those 8 pixels that we just created into 16, making those 4 bits into an 8x2 pixel swatch. So each bit is a 2x2 swatch of pixels, just like we want. And I will say again, this changed recently as well in order to support the big endianness. But I guess that's all I really need to say about that. Okay, so hang on, stay with me here. So we do that for both sets of 4 pixels in every byte in order. Once we're done, one entire section of the memory in the screen driver is filled with a scaled up image of the new board that we want to display. So once we are all the way through this here, we have recreated a scaled up image of the new board inside of the memory of the screen. So all that's left to do is tell the OLED to show that section of memory, which is what this line does. And so this is one of those nice things that Tiny 4K OLED does for you. The SSD1306 driver has no concept of this double buffering, so it's all inside of Tiny 4K OLED. So the switch frame switches both frames. There's a render frame and then there's like a memory frame. And so that's how those frames are out of sync, and that's how we do this double buffering thing, is when we call switch frame, it switches the render frame to the frame that was just the memory frame, and it switches the memory frame to the frame that was just the render frame. So now the screen shows the new memory, and then you have a whole new block of new memory that the screen isn't looking at to write to. So once that's done, if you remember, way back up here, we get down to here, and then we immediately loop back to the top, and we start working on the next frame, iterating over the pixels to compute their next value. That's it. Congratulations for getting to the the end of this video. I know this was a lot of info. Don't worry about getting everything in one go. Feel free to skip around, come back if you need to. Also, if you're confused by any part, please leave a comment below, and I will do my best to get back to you. I'll leave the links in the description to any helpful documentation I've found. Thanks, everybody. Have a good one.